Yeah. So, in this hopefully short module, we will talk about Alexandrite and fibril lasers. So, this is what we had discussed in the previous module. We are introducing a very new discovery, LED pumped Alexandrite lasers. And of course, if you can pump with LEDs instead of diode pumped solid state lasers, that is beneficial in many ways, including cost and ease of operation. So, what we said is that you have these 450 nanometer emitting LEDs that are used to build luminescent concentrators. So, let us, before going further, talk about what luminescent concentrators are. Once again, this is not a very new idea. This idea has been around for a long time, and it is a popular research topics for materials chemists, material scientists. The idea is this: you have a solar cell. Okay? In order to capture solar radiation, what do you want? You want a large surface area, isn't it? But many times you also want to concentrate the solar cell you have captured. If you think of more futuristic kind of applications, we have a window, right. Let us say I want my window, I have big windows in a house, I want these windows to act as solar cells, which means the sunlight that falls on the windows, I want to capture it and I want to utilize the energy. How will you do it? In the conventional design of solar cells, if you put panels there, then your window is going to become opaque, right. So, is there a way of having a transparent window, perhaps, maybe colored, but transparent nevertheless, but something that captures energy very efficiently, and that will be nice in another way as well. If the sunlight is completely absorbed and the energy sent somewhere else, then your room will remain cool. Okay? That is the idea, and that is what has been utilized here. So, the idea is this: in case of solar concentration sunlight, in case of the application we are talking about, light from the LEDs comes from this direction. So, this is your concentrator. So, you place the LEDs here, and that is why there are several designs of LEDs. I mean, you have also seen, right, Diwali is coming. During Diwali, people use this long strings of LEDs and all, but you also have the square LEDs, right. Square LEDs are convenient because if you take something like a slide, let us say, okay, microscope slide, you can place the LEDs one by the other, right, and completely cover the surface. So, now imagine a situation where you have something like a glass slide, well, something like this. On top you have LEDs facing downwards, giving out light. At the bottom you have LEDs facing upward. So, from both sides the light from the LEDs falls on the substance of which this slab is made of, right. Now, in this slab what you have is, you have emitters which absorb the LED light, and in the ideal case scenario with quantum efficiency of 1, quantum yield of 1, emits the light as well in whatever their emission range is. Okay. Then what will happen? Typically, this medium in which the emitters are embedded, that has a higher refractive index. So, if higher refractive index here, lower refractive index here, then what will happen? Many times when light is emitted, it is going to undergo total internal reflection, right. So, that is what is shown here. You see these squares, what it means is, at the junction you have an emitter, or maybe here you have an emitter. Emitted light hits this wall, then here, then here. So, it goes in a zigzag fashion until it can go out from the side. Understand what I am saying? So, if total internal reflection is 100%, it is never 100%, the design is very critical here, but in this case, in any case you are covering the surfaces by LEDs. So, if no emitted light is allowed to go out from this direction, and let us say in this side I have polished it, so it acts as a mirror, then what will happen? The only place from which the light can come out is this face. Okay? So, you have directional emission. Directional emission is once again a very important topic of research that has been going on for the last 7-8 years. Lakovich among others has done a lot of work there, in our own city in BRC, Sharmishra Datta Chaudhary works in that direction. Okay, have you understood what's going on here? So, this is a very efficient way of concentrating the light. The light is being captured on this surface and that surface, and it is being emitted from a much smaller surface. So, naturally it will get concentrated, right. So, that is what is used to deliver a high dosage of light to anything that you keep on this side. This is how a concentrator works. Are we clear? And different people try different things. Organometallic complexes, organic molecules, nanoparticles, that is these things are different choices for the emitters, and what is the substrate going to be, that is another question. Because ideally what you want is, you want quantum efficiency of 1. The emitter should be such that it emits with quantum efficiency of 1, and also total internal reflection should be the thing that if only 10% light gets totally internally reflected, then it is of no use. Okay. This is how a luminescent concentrator works. So, the reason why I wanted to digress and talk about this is that this is really an important topic of current research anyway, not only for people working in optics, but more so for chemists. Most of the time chemists are working on things like this. Okay. Now, let us come back. So, now you know what this is, luminescent concentrator. Now, where will it emit? It will emit in the region where the active component cerium YAG emits, and that is this big fat emission spectrum. As we have said in the last module, this emission spectrum has very strong overlap with the absorption of Alexandrite. So, if you place it correctly, and we will see how it is placed, Alexandrite will you can transfer all this energy to Alexandrite, and then the emission of Alexandrite is stimulated emission from Alexandrite is what is used to make the laser. Remember, the laser we are talking about right now is not a pulsed laser, it is a CW laser. In fact, this application that is shown in this diagram, there this Alexandrite laser is used not as an oscillator, but as an amplifier. And since it is an early report, the Tisapphire laser that is used as an oscillator, you can use Alexandrite as oscillator as well. I am sure it is there, or it will come very soon. So, you take the light out of this continuous wave Tisapphire laser, and then see this design, maybe see this one at the bottom. So, this green thingy is your luminescent concentrator, okay. And we said it will all the light will come out from one direction, that is where the Alexandrite rod is placed. So, it is a beautiful design, and the dimensions are such that the Alexandrite rod completely covers that end. So, whatever light comes out of this luminescent concentrator has to be used to pump that Alexandrite crystal that is there, Alexandrite rod that is there. So, that is a really nice design. Then it has been shown that it can act as an oscillator, of course, but here it is acting as an amplifier. What kind of amplifier? Multipass amplifier. So, you see this? So, light goes in, gets reflected here, comes here, goes out, and then it hits a mirror, gets sent back. This way it does many passes until it goes out after amplification. Okay. This system is not there in the market, but maybe when you set up your independent labs, you are going to use things like this. And I hope you understand that this also would lead to a significant amount of miniaturization, compression of size. Okay. Now, that being said, let us not go home with the impression that you cannot make ultrafast amplifiers with Alexandrite. In fact, you can, and as early as 1996 there have been reports. Once again you see Square's name here. Square has done a lot of work in this direction. So, there what they did is 200 femtosecond pulses from Tisapphire oscillator was amplified to millijoule level. Okay. And then read the last line if you can. This system also amplified femtosecond pulses from a frequency doubled erbium doped fiber laser. So, that is the other kind of laser we want to talk about, we will get there. This is the design. You have tri-sapphire laser as the source, it is not even shown here. You have a stretcher, you have a compressor here, optical isolator is what separates the incoming and outgoing beam, and here you see this pump laser is also Alexandrite, diode pumped Alexandrite laser. So, it is DPSS, and the Alexandrite rod is used as the gain medium in the amplifier. Okay. And here you can see the autocorrelation trace, and that is, I think, if I remember correctly, 300 femtosecond or so. Okay. Now, so that is what we wanted to say about Alexandrite. Another class of lasers which has actually been marketed for a significant amount of time now is ultrafast fiber lasers. We will not do a very thorough discussion, but at least to get an idea about it, you can read this review in Nature Photonics by Furman and Hartle. You might have noticed that Furman also featured in the 1996 paper on Alexandrite lasers. Now, ultrafast fiber lasers are marketed by, I think, 40 companies now. So, it is not as uncommon as Alexandrite, even Alexandrite is not so uncommon, but ultrafast fiber lasers are catching up big time. And one reason why you might want to use ultrafast fiber lasers is that first of all they are compact. You have a say 10-foot long fiber, not 10 foot, let's say you have a 30 feet long fiber. Do you need a table that is 30 feet long to keep it? Right? You can just coil it and keep it in a small box, or even leave it on a table, provided you do not have people in the lab who are going to go and hit it with a hammer or something, right. That is why it is very simple. And also in the last 20 years, I would say this connecting fibers, maintaining polarization in fibers, splicing fibers, all this has become very easy. Nowadays you can buy reasonably cheap accessories with which you can make all sorts of combinations of fibers. So, ultrafast fiber lasers are actually coming up in a big way. Now, in these lasers you usually have two kinds of fibers. One is you need an optical medium. For that you have a small stretch of fiber, usually you can have the entire fiber like that, does not matter, but usually you have a small stretch of fiber that is doped with something like an lanthanide ion. That is your gain medium. And then you have polarization maintaining fiber that makes up the cavity. Okay. So, I will show you one design, there are many, and this design is again from this 2012 paper, and you will see the moment we go into fiber lasers, our line of thinking is a continuation of what we have done so far for free space lasers, but new things start coming in. So, here in this figure itself, do you see the active media? Do you see the gain media? Yeah? The one in different color? YB fiber? That is a gain medium, doped fiber. Rest of it is just simple polarization maintaining fiber. So, this fiber works in two stages, and you see where the difference comes. First of all, this gain medium, fiber gain medium is pumped by 980 nanometer light, and here you see there is a combination, it is like railway tracks, right, one coming in and joining the other one. This coupler that brings in a different wavelength of light is called a WDM, wavelength division multiplexer. It can also be used to divide paths of two fiber of two kinds of light. Okay. So, that pump light comes in and then pumps this YB fiber, and initially you get CW operation. We are isolated and all, we do not have to talk about that. Here we see there is a 60-40 coupler. 60-40 coupler means 60% of the light goes straight, still CW, 40% of the light enters this small loop. What is there in the small loop? It is sort of like, it is amplification, and this is not amplification maybe, this is where mode locking takes place in the smaller loop. Once again you have a pump, the 980 nanometer comes in, and 1030 nanometer is the radiation, the frequency of the wavelength of the light that you get out from this laser. Again you have this YB fiber, it is pumped by this, and then you get the output of this coming in here, and in this loop you place a mode locking element. The mode locking element that has been used here is called a NALM, nonlinear amplifying loop mirror. But I understand better, because I do not know so much about fibers, I understand better if I replace this by something like what we have discussed, saturable absorber mirror. Remember saturable absorber mirrors? First you have a Bragg mirror, where light goes in and comes out, and when that happens mode locking is achieved, because only light that is in phase survives, everything else is eliminated. And then we said that you put a quantum well in front, you get a passive mode locker. So you can put in something like that. So mode lock light comes and joins the loop here, and here you have an 80-20 coupler, 20% goes out, 80% goes back in the loop. This way it is. So you see the philosophy is the same, but with some additional components, okay, and there are other designs as well. So this is more or less what fiber laser, how a fiber laser works. And then just to complete the discussion without going into too much of detail, you can in principle make an amplifier out of it, and in fact all fiber amplifiers are marketed already by several companies. Now one thing that is very much there is that generally these optical fibers with which lasers have been made so far, they all work very well in IR. Most of this fiber was made first of all for optical optical communication. I remember sometimes we do not have internet because somebody has hacked the fiber underground. So that is the telecommunication is why optical fibers became important. So here also most of the lasers have been built upon similar same fibers. So usually you get an IR laser, and then it has to have sufficiently high power so that you can get second harmonic, third harmonic, fourth harmonic to get visible light, or if possible UV light. In this design that we have shown, all this is fiber, but then to get a short pulse you have to use a bulk grating compressor. So do not think that we have achieved a situation where it can be fiber and nothing else. It is there, but if you want good performance, many times it is a combination of optical fibers and more conventional components like gratings or prism pairs. So ultrafast fiber lasers are coming up big time, and well, companies who market them of course would like to see them replace Teissifier completely. That has not happened so far, but if it happens, as we have discussed already, there are several advantages. Perhaps you do not even need a very clean lab if optical fibers rule the roost. One thing that I should say is this, here there is an issue with using optical fibers if you want to make an ultrafast laser. Can somebody tell me what it is? What do we have in the optical fiber? Is it free space? Then it is solid, right? Something like glass. Yes, dispersion is a very major problem. So that is why you do not see a stretcher anywhere. When you use an optical fiber, the pulse is stretched anyway. Stretching is not a problem. So you have to compress it. Compression is a more important thing. That is why, see, for compression they have used a grating. It is not so easy to do it otherwise. So it is, on the face of it, it might seem to be a disadvantage because it gets stretched, but as we know, if you are going to do chirp pulse amplification, we have to stretch the pulse anyway. So, actually it turns out to be not such a bad thing after all. Okay. So, what we have done in this module and the last one is a very preliminary discussion of ultrafast lasers, and in one case CW laser beyond Ti-Sapphire. This is not even the beginning. If you want to really learn about these systems, there is no dearth of papers, no dearth of manuals, no dearth of material on the web. Be my guest, but for the purpose of the course we will stop the discussion here, and then we are going to next talk about what we have in our lab.